Let's start with a brief overview of web APIs and REST in general. Here's some of the resources we used in this presentation. If you find them useful, feel free to check them out. So starting off, web APIs are everywhere. So they're found in public APIs covering all kinds of sectors, business sector, of course, social media, scientific sector, the public sector, pretty much any segment you can imagine will probably have some type of a web API that's representing it in some way. Internally, in with microservices and enterprise systems within a business, REST APIs, web APIs are used pervasively, and of course, they're often used to drive mobile and web UIs, acting as, in this case, the front-end APIs for those user interfaces. So if you check out programmable web here, you can see the large amount of APIs that you can find out there, grouped by categories, by protocols, all kinds of different things. Let's experiment with some of the public APIs that are out there to get some hands-on experience. So let's go to the programmable web website, check out what it has available to us so we can play around with some of the APIs that are out there. So we can do an API search. How about we search for NASA Mars weather? And they do have one. NASA Insight Mars Weather Service. So it says that the NASA Insight Mars Weather Service API allows developers to get summary data for each of the last available Martian days. This data is provided by NASA's InSight Mars lander, which takes continuous weather measurements on the surface of Mars. Measurements are taken at Elysium Planitia near Mars's equator and include temperature, wind, and pressure. So let's go check that one out. We can go to, we can go directly to the endpoint, or we can go to the portal homepage. Let's go to NASA's portal. They've got a number of APIs that they have available. The Insight one that we looked at is this one here. And it gives us a summary again, which we read before. Here's a picture of Insight and some of the data that it's collected as an example, shown in a web page. So here they talk a little bit more about how you can call the API. This is a relatively simple one. Basically, you can make a request to api.nasa.gov Insight Weather, providing an API key, and we will use the demo key provided by NASA, specifying a feed type. We'll use JSON and a version number of the API 1.0. So as an example query, we could click this link here. We'll just do that actually and see what we get. And indeed, we do get a JSON representation of the wind, pressure, temperature readings over on Mars taken by InSight over the last 7 Martian days. NASA's also mentioned that there's a self-contained HTML document which renders the data that comes from InSight into a windrows pattern like this. So that sounds kind of interesting. This basically fits the use case scenario that we were talking about earlier when we said that oftentimes APIs are used to drive web UIs, mobile UIs. So that's exactly what NASA has done here. We might as well go check that out and see how they did that. Let's click here and we'll go to, here's the page with the windrows. It's apparently automatically downloaded the data from the API as soon as the page loaded. That's fine. What I'd like to do is to go see how all that was done. How is it that this web page reaches out to the API, pulls down the JSON data, and ultimately renders this plot? So let's see how that's done. And we can use some of the tools that are built into the browser. We can go to More Tools, Developer Tools, and we get a side panel here that represents basically or allows you to track everything that's happening behind the scenes on the web page that you're currently on. So we can do that. I've got the network tab in focus right now. So I'm going to come back here and refresh this page and see what documents got downloaded. And we can see there's the main HTML page itself, a few other JavaScript libraries, but the one that's interesting to us is that apparently the web page did go ahead and on page load ended up reaching out to the API's endpoint and pulling down the data. And we can see that over here by clicking on the link that the web page had pulled down. And sure enough, here's the JSON response that came back from that web API. So what I'd like to see is how does the browser go about doing this? And we're not going to spend a lot of time looking into great detail how the JavaScript works on this page, but we'll look at it at least qualitatively, if not quantitatively, to see how exactly the web page ends up acting as a client to this web API. So we can do that by going to the sources, and here's the various sources that make up this web page. The web page itself happens to have all of the JavaScript on there that we need. So we just click on the web page itself and we scroll down a bit. We can see here is the body of the HTML page, and we see it's immediately followed by a script element, which means that anything in this script tag is going to be executed in line, which is what we saw. If we go down a bit farther, we see that sure enough, when this script tag is parsed in the browser, we end up here at a GET request using a JavaScript library that allows us to reach out to web APIs. And it's making a web request to api.nasa.gov here. So let's go ahead and set a breakpoint here, and we'll refresh the page and see how the web page is actually consuming this data that came down from the REST API. So we set our breakpoint, and this time, before the whole page is rendered, we stop at the get call. So let's take a look here and see what's happening. So the get call, when it completes, if it completes successfully, it gathers the data that came back from that web call and sends it to another function block, another code block, which is right here. So we can start with that. Let's just set a breakpoint here. And when the web page returns, we should be in this code block, and we'll see what the web page is doing with the data that returned. I also noticed that there's another block that's going to get executed. It says it's always going to get executed, so we should probably set a breakpoint here as well. And then we'll just hit continue. So we've got a return back from the web API. The browser now has the data. In fact, I think I could probably look at the network console and see that we did actually issue the request here. But going back to our sources tab, we can debug. I can hover over the data element that was returned from the API call, and we see what we would expect, I believe. And what's apparently happening here is that the data payload is being iterated over. All of the Martian days are being iterated over one by one and sent to a function called write sol data. So let's take a look at what write sol data is doing. I'll just put it in my clipboard and search for it. Let's set a breakpoint here and continue. And then we'll just step through a little bit and see what's happening in the UI. So it looks like with each solar data, we're rendering a button. And we can just continue from there. And the buttons are rendered, so let's continue. And we end up in the always clause that we saw at the beginning. And that is where we're going to actually plot the data. So let's step over that. And we see we end up in a function called plot sold data, which sounds interesting. Let's just put that in our clipboard and search for it. And we'll set a breakpoint here and continue. And let's see what plot sold data does. Looks like it's turning the data into something that is easily plottable by the plotting library. And now we come across the point where we're actually going to issue the call to the JavaScript library that plots the windrows for us. And sure enough, there it is. So that's an example of a web API driving a web user interface, which again is one of the very common scenarios that we talked about earlier for web APIs. It's often useful to be able to experiment with HTTP from the command line. It can be a great debugging technique, but it's also useful just to get a feel for what an HTTP request and response look like. We'll use the command line client HTTPI to do exactly that. If you want to try it out for yourself, it's available at httpi.org. Let's give HTTPI a quick spin so we can take a look at what happens with an HTTP request at a low level. So here's HTTPI making a request to httpbin.org, which is a nice site that's set up to allow people to test their HTTP clients. It has a set of endpoints like get, put, post, delete, and in this case we're just pointing HTTPI at the get endpoint for httpbin.org, and we see a set of headers that are sent by us, and we get a response back, HTTP 200 OK, which is good, and a set of response headers and the payload itself. We can do other things as well. We're not limited to just get with HTTPI. We could also do a put. And in this case, with the put request, we're going to send a payload. So we'll send the payload of hello world, and we get a response back from httpin.org that simply echoes the payload that we sent in the first place. And there's other ones you can use as well, obviously. Let's do a teardown of an HTTP request now that we've seen a few of them in action. So this is a relatively simple request. We are going to, using the HTTPI command line utility that we saw earlier, we made a request to httpbin.org's get endpoint, passing it hello equals world query string. This is the result that we got back. Let's break this down to see what was happening behind the scenes. So we made our request. That's the URL here that we issued. And breaking it down a little bit, there's a path parameter that is part of the URL. The path parameter is just the part after the host name and before the query string. So in this case, it's really small. It's just /get. The query string follows the question mark. In this case, it's hello equals world. Typically, a query string is a set of key value pairs separated by an equal sign. If there's multiple of them, they're separated by an ampersand. In this case, we just have one set of key value pairs, so it's hello equals world. And query strings are often used to filter results that come back from a web page. The next part of the HTTP request are the request headers. So that is a line delimited set of key value pairs separated by a colon. So in this case, we have 1, 2, 3, 4, 5 request headers that were sent along with the request automatically by HTTPI for us. And then comes the request body. Gets typically don't have a request body, so it's blank for us. And then that was sent off to the server and we got a response back. So everything in blue is a response back. First thing that comes back is the HTTP status. Everything was good, so it was reported as 200 OK. Then the set of response headers that come back, again, key value pairs delimited by a colon and then line delimited between each other. Then a blank line, you can see here a little bit, followed by finally the response body itself. And in this case, the response body was a JSON payload, but it doesn't have to be. So that's basically a breakdown of an HTTP request and response. These are the pieces of a request that you end up working with as an API developer. So you see things like a query string, you see things like the path, and typically you'll use that information to change the behavior of how your API is going to behave. It's going to work. So that gave us a chance to get our feet wet, if you will, by checking out some of the APIs that are available out there um, and trying them out live, either in a web browser or with a command line tool to see what's available in some of those APIs. Another thing we wanted to cover is what types of APIs. And there are different types of web APIs out there. REST is the most well-known, but there are other ones as well. REST Hybrid, which is mostly REST, but maybe doesn't adhere to all of the constraints that are mandated by a truly REST API. Then there's RPC, which is basically remote procedure calls over HTTP. And there's other ones as well, GraphQL, which is really adept at being able to query data sources. gRPC, which is very efficient and runs over HTTP2, and of course the venerable SOAP, among other ones as well. Let's take a look at what are some of the differences between some of these API styles, just to get a feel for them. An RPC style would look something like this, and you would basically be doing a remote procedure call into some function, some subroutine maybe, on the server itself. So here we've got sending a post request to an endpoint called subroutine read customer. In this example, read customer in pseudo code might look something like this. It simply takes an ID and reads a record from the database from the customer file based on that ID and returns as an output parameter the record that was read. And so that would look something like this, where the input parameters, at least to that request, would be probably JSON encoded, although they could be XML encoded. But in some fashion, the body of the post request has encoded the remote procedure call parameters. So in this case, our example, we've got ID 1001 being passed to this endpoint in the payload, the post request. So interesting thing here to note about RPCs that they're action oriented, meaning that actions like read customer or list members, delete order, those are the sort of the first class, they're first class members of the architectural style that is RPC. Contrast that with REST, which we're going to look at now. REST is quite a bit different. In this REST request, we're doing pretty much the same thing that we were doing before conceptually. We're making a request to a server and we're asking that the record that exists at 1001 in the customer's resource be returned. Basically the same thing we did with our post subroutine request over RPC just a moment ago, but you can see the URL looks a lot different. And the reason for that is that REST, unlike RPC, is resource oriented. Again, RPCs are action oriented, but REST deals with resources. So you can almost think of it as more noun driven, where resources are the nouns that you're going to work on, contrasted with RPC, which is more verb driven, where the actions are the verbs that you want to have happen, that you're requesting to have happen on the server. So REST again deals with resources. So resources like customer, order, or product. Then the question is, what actions can you perform on those resources that are served up via a truly RESTful API? So the actions that you get are a fixed set of actions, and they're represented by the HTTP verbs that are available over HTTP, like get, put, post, delete, patch, a few others. So those verbs map more or less to the CRUD actions that you would imagine would be legal to do against a resource. So what kind of things could you do against a resource where you could create them, you could update them, delete them, read them? And those CRUD actions are represented again by these HTTP verbs. Like if you wanted to read, you would do a get. If you wanted to do an update, you would do a put. If you wanted to do a delete, of course, you'd do a delete. If you wanted to do a create, you would do a post. And there's some other ones like patch, which are sort of like partial updates to a resource on the server. So again, they do look quite a bit different than an RPC style. So this is basically if you wanted to update the resource at this URI, you would issue a put request to it, supplying in the payload to that put request the parameters that needed to be updated on the data server. With a post typically again is associated with adding to a set of resources. So in this case with the post, you typically don't specify an ID because you're posting to a collection. And inside the payload to your post request, you would end up having perhaps the ID that you wanted to actually create in the database, or maybe the database would be in charge of allocating that ID itself. But this is how you would actually create a new resource under the customer's collection. And deleting, of course, you would need to send the ID of the resource that you wanted to delete. So we know there's different types of APIs out there now. Um, the question is, why doesn't everyone just use REST? That's obviously the most popular of all the API styles out there. And there was a period of time when if your API wasn't 100% RESTful, you might get a red mark against it. I think we're a little more pragmatic about it nowadays, and there came the realization that there, depending on the needs of your API, you may or may not want to make your API 100% RESTful, or in maybe more extreme cases, you don't even want to have it be very RESTful at all. Maybe you use something like RPC or GraphQL or gRPC, which have their own strengths. So the question as far as what type of API you want to end up developing probably revolves around the question of who uses your API and why. Once you have those questions answered, then you're well on the way to deciding what type of an API that you want to implement. So before we wrap up, I did want to spend a little bit of time on what REST is, because again, it is the most popular API style out there, and it's probably important to be able to see what exactly makes a truly RESTful API. First and foremost, it is an architectural style. It's not a protocol. It's not something like SOAP that you would implement via a library. It's really just an architectural style that is supposed to work the way the web works. Um, we'll see examples of that in just a minute when we look at the constraints that are required for your API to be truly RESTful. But first, let's see where did the word REST come from? So it came from a paper written in 2000 by Roy Fielding, and it was coined from the phrase representational state transfer. That in and of itself isn't the most uh, intuitive term, so we'll try to break it down a little bit and see, where exactly that term came from. So if you remember so if you remember how REST depends on, so if you remember how REST works with resources owned by the server. So the client and the server, when they interact with each other, they work with these resources. And those resources have agreed upon representations. A representation in a web API might be that the resource is encoded in JSON or XML. In the case of a more traditional web server, then the representation might be an HTML page. But the point is, the resources can have different representations, and the client and server agree upon what those representations are. When the client and server then begin to communicate, they communicate by transferring the state of the representation to their counterparts. So, for example, to make it a bit more concrete, if a client requests a resource from a server, the server encodes that resource into a representation where it has a certain state and sends that representation down to the client, transfers it down to the client. The client then may want to make a change to that resource, so maybe it'll take the last name. The client may want to make a change to that resource, so it might take the representation and change, for example, the last name field in a JSON document to be Smith instead of Jones. Once it does that, it transfers this new state of the resource back up to the server, maybe via a put request, and the server acts on that new state, presumably saving it into its data source. So those are where the terms come from. That's where representational state transfer comes from. It's around the fact that client and servers communicate by sending representations of resources to each other, and when they want to change change the resource in some way, they change the state of that representation and transfer the new state to their counterpart. So let's take a quick dive into the architectural constraints of REST. Again, these constraints are in place because they're intended to help your web API act the way the web acts, behave the way the web behaves, so that your API goes with the grain of the web instead of against it. So the first one is client server. That one's fairly obvious, especially when you go back to thinking in terms of especially when you go back to thinking in terms of web servers and browsers. Obviously, there's the browser is the client and the web server is the server. When you get into web APIs, the reason client server is so important is it allows a clear separation of concerns. So that's why you'd want to make sure you meet that first architectural constraint. The second one is that REST architectures are stateless. That can be a little bit confusing because we saw that state is a key word in the acronym REST in the first place. So it seems a little strange that we would call it stateless. But keep in mind that the state that we're talking about here is not the state that is transferred back and forth. The, it's the state that the server could, if it wanted to, save for a client. But that's not allowed in a RESTful architecture. The server is not allowed to save any client context in between the requests that a given client makes. So when a client makes a request to the server should be allowed to forget about the client. And if the client comes back later and makes another request, the client needs to supply any information that the server might need to be able to properly interact with it. So nothing is stored on the server. Cacheable is the other architectural constraint. So just like web pages can be cached, web API results can be cached, and they may be cached either on the client itself or they could be cached by intermediaries between the client and the server. Which brings us to the next architectural constraint, and that's that REST systems are layered systems. And that just means that intermediaries may exist between client and server, but they're going to be invisible to the client. The client always just thinks he's talking directly to the server, even though there may be proxies or load balancers somewhere in between, and those proxies may cache, but the client isn't concerned with that. And the last big architectural constraint around REST is the uniform interface. The uniform interface has a number of subtenants, and it can be relatively complicated, so let's just go through them one by one here. The first one is around resource identification. So that simply means in terms of web APIs that the resources that are served up by a web API server are identified via URIs, just like we see in the example here. Resource manipulation is the next constraint of the uniform interface, and it simply means that resources are changed by representation. It simply means that resources are changed only by representation transfer. And it really gets down to the RESTful. It really gets down to the RESTful acronym that we learned about it at the a few seconds ago. And it really gets down to the RESTful acronym that we discussed a minute ago. Further, those representations are transferred via standard HTTP verbs like get, put, post, delete, patch, etc. Self-descriptive messages is another important aspect of the uniform interface. What it really means is that a message that's passed between the server and the client and vice versa has everything contained within it that the counterpart needs to be able to process it. So, for example, let's take this example that we see here. Here, the client is issuing a request customers to the customer's endpoint looking for customer number 1001, and the server responds with a JSON payload. But the server needs to make sure that it tells the client that the payload is encoded in JSON format. And that way the client doesn't need to make any assumptions that it should parse the payload with JSON versus any other parser, XML, anything like that. The server outlines exactly what the payload is so the client knows precisely what to do. And lastly, probably the most complicated of the tenets of the uniform interface is the hypermedia as the engine of application state. And what that's really saying is that when a server responds with a resource, the server should include in that response all of the sub-resources that a client may need to interact with. So in this example, the client has asked for all of the customers at the customer's endpoint, and the server has dutifully responded. But with each customer that it sends down, it also sends the URI where that customer resource lives. So why is this important? It may seem unnecessary because it seems a bit intuitive that, well, if you have a customer's endpoint like this, then to reach an individual customer, you would just need to put the identifier at the end of the base URL and you would be good to go. But that's where Hypermedia as the engine of application state comes in, and it says you can't ask the client to make that assumption. You need to explicitly say that the client can find the sub-resources at these particular endpoints. And basically that's where Hypermedia as the engine of application state comes in for a RESTful API. The last one that I didn't really cover is number 6, which is that which is code on demand. That's an optional feature of the REST architecture, and it was really to deal with web servers sending down HTML pages accompanied by JavaScript code. It doesn't apply quite as much to web APIs, and so it's considered an optional part of the architectural constraints for REST.